In a dark optics lab, a single photon faces a choice. It can travel one path, another, or both. The physicists controlling the experiment wait to decide how they'll measure it. But that decision happens after the photon's flight. When they finally look, the result matches their later choice, as if the particle anticipated it. These are real delayed choice experiments first proposed by physicist John Archibald Wheeler. Modern versions in Vienna and Maryland use high-speed detectors to test whether the act of measurement itself shapes the past. The outcome suggests a strange symmetry. Events in the present may depend on conditions set in the future. Quantum mechanics has always lived with paradox. Richard Feynman once described antimatter as matter moving backward through time, an idea that made the equations work. Decades later, Yakir Aharonov took the hint seriously. He and his team developed the two-state vector formalism, a model where every quantum event carries two waves, one from the past, one from the future. When those waves meet, the result becomes real. Reality, in that view, isn't built step by step. It's negotiated between two temporal boundaries. The photon doesn't just respond to what was prepared. It also knows how the story ends. Laboratories are still testing this framework. Post-selection experiments, where scientists keep only the runs ending in specific outcomes, show patterns that appear coordinated across time. The mathematics allows it. The particles seem to cooperate. If these correlations hold, they hint that the universe could be time-symmetric. The laws work both forward and backward, even if our senses can't follow. Most physical laws, gravity, electromagnetism, Schrödinger's equation, look identical whether run forward or backward. Only entropy gives us direction. Philosopher Hugh Price calls this time-symmetric physics. He argues that the arrow of time may not be fundamental but statistical, the large-scale result of disorder increasing. On the quantum level, the rules could be reversible, with the past and future equally real. This symmetry could solve the mystery of quantum measurement. Instead of a wave collapsing when we observe it, the outcome might be fixed by two matching conditions. One set when the experiment begins, another when it ends. The wave doesn't die, it simply satisfies both. Information, then, isn't lost but shared across time, a constant conversation between history and destiny. Skeptics remind us that no one has sent a message to yesterday or changed a recorded event. Retrocausality remains an interpretation of the math, not a proven mechanism. But even as interpretation, it shifts perspective. The universe stops looking like a line of dominoes and starts resembling a woven fabric, every moment connected to every other. Aharonov once said quantum mechanics is not about uncertainty, but about correlation between what was and what will be. When the next photon races through its maze of mirrors, its destination may already be encoded in the same timeless pattern that defined its start. Time itself might be less a flowing river and more a standing wave, rippling from both directions. If that's true, the present is only the place where two invisible tides meet. One from the birth of the cosmos, one from its distant end. And somewhere in that interference, the future may already be watching.